There is a kind of silence that comes before the brightest explosions in the universe. From the outside, the star may still look ordinary. It may hang in the sky as a blue-white point, steady, distant, almost serene. Its surface may still be shining with the same light it has poured into space for millions of years. If there were worlds nearby, they would still be warmed by it. If there were oceans beneath that light, they would still reflect it. Nothing in the starlight would announce that the center had already crossed a line from which no signal, no correction, and no miracle of pressure could bring it back. Deep below the visible surface, in a region buried under layers of hydrogen, helium, carbon, oxygen, neon, and silicon, the star has made something it cannot use. It has built an iron heart. That sounds almost peaceful. Iron is familiar to us. It is in blood. It is in stone. It is in the core of our planet and in the tools we once used to cut open the world. But inside a massive star, iron is not a foundation. It is a warning. For millions of years, the star has survived by turning lighter nuclei into heavier nuclei and taking the released energy as its defense against gravity. Hydrogen bought it ages. Helium bought it less. Carbon, neon, oxygen, and silicon bought it only shorter and shorter reprieves. But iron is different. Fuse iron, and the star does not gain energy. It loses it. The last furnace has reached ash, and in that moment, the familiar picture of a supernova as a star blowing outward is already misleading. The first motion is not outward, it is inward. The true beginning of the explosion is an implosion, a collapse so fast that a core roughly the size of Earth can fall toward the size of a city in less than a second. Matter is driven to densities where atoms cannot remain atoms, where electrons are forced into protons, where neutrinos escape in a flood, and where the core becomes something closer to a giant atomic nucleus than to any matter we know on Earth. The surface has not yet noticed. The light has not yet changed, but the star has already died in its center. The question is not simply why stars explode. The deeper question is how the universe turns a failure of support into a mechanism of creation. How does inward collapse become outward fire? Why do some dying stars leave neutron stars, some leave black holes, and some dead stars explode so completely that nothing remains? And why is the material in your blood, your bones, and the ground beneath you tied to these last seconds of stellar life? A supernova is not just a detonation in the dark, it is a transfer. It is the moment when matter that was locked inside a star is thrown back into the galaxy, changed, enriched, and made available for something that did not exist before. But to understand that generosity, we first have to enter the star before it dies, while the war is still balanced and the ending is still hidden. A star is not a fire in the ordinary sense. Fire on Earth is chemistry. It is atoms rearranging their electrons, releasing energy because carbon and oxygen prefer to become carbon dioxide. A campfire burns because molecules find a lower energy arrangement. A star works deeper than chemistry. It lives by rearranging nuclei. At its center, the pressure is so high and the temperature so extreme that matter becomes plasma. Electrons are stripped from atoms. Nuclei move through a sea of charge. In a star like the Sun, protons are forced close enough that nuclear reactions become possible, even though the positive charges normally repel one another. When hydrogen fuses into helium, a small amount of mass becomes energy. That energy is not poetic language. It is the pressure that keeps the star from collapsing under its own weight. This is the first important balance. Gravity pulls everything inward. Fusion produces heat and radiation that push outward. When those two tendencies match, the star enters hydrostatic equilibrium. It is not peaceful, but it is stable. Every layer of the star feels the weight of the layers above it, and every layer is supported by pressure from below. If pressure rises too much, the star expands and cools. If pressure falls, gravity compresses the star and heats it. In ordinary stellar life, this feedback acts like a thermostat, but the thermostat has a limit. It works only while the star can find fuel that releases energy. The mass of the star decides how long the story lasts and how it ends. A low-mass star spends its fuel slowly. It may burn for tens or even hundreds of billions of years. A star like the Sun lives for roughly 10 billion years on the main sequence, steadily converting hydrogen into helium in its core. When the Sun exhausts its core hydrogen, it will swell into a red giant, fuse helium into carbon and oxygen, and eventually shed its outer layers, leaving a white dwarf behind. It will not become a core collapse supernova. It is not heavy enough. A massive star lives by different rules. It has more fuel, but it burns that fuel at a far higher rate because its gravity crushes its core harder, raising the temperature and accelerating nuclear reactions. A star 20 times the mass of the Sun may shine not 20 times brighter, but tens of thousands of times brighter. It spends its wealth with terrifying speed. Its life may last only a few million years, a brief flare compared with the Sun. At first, it burns hydrogen into helium, as all stars do. The core is hot, the pressure is strong, and the outward flow of energy holds gravity back. But eventually, the hydrogen in the core is exhausted. Fusion there stops. The core contracts. As it contracts, it heats. Hydrogen continues to burn in a shell around the core, but the center itself is now mainly helium, compressed and waiting. At about 100 million degrees, helium can fuse. 3 helium nuclei can ultimately form carbon through the triple alpha process, with an unstable beryllium stage that exists for only an almost unimaginably brief moment. Some of that carbon can capture another helium nucleus and become oxygen. In this quiet interior stage, the star is building 2 of the elements that will one day be central to planets and life. But even here, the clock has accelerated. Helium burning lasts far less time than hydrogen burning. When helium runs low, the core contracts again. It becomes hotter. Carbon can ignite. Carbon burning produces elements such as neon, sodium, and magnesium. But carbon burning in a massive star is not an age of stability in the way hydrogen burning was. It may last only thousands of years, then carbon is exhausted. The core contracts again. Neon burning follows, then oxygen burning, then silicon burning. Each stage requires a higher temperature. Each stage produces less useful energy. Each stage lasts a shorter time. This is one of the most haunting facts in stellar evolution. The life of a massive star does not end at a constant pace. It accelerates toward collapse. Hydrogen may last millions of years. Helium may last hundreds of thousands or 1,000,000 years, depending on the star. Carbon may last centuries or millennia. Neon may last years. Oxygen may last months. Silicon may last days, sometimes less. The star is not merely aging. It is running down a staircase where each step is shorter than the one before. By the end, the star is layered like an onion, but the image is too gentle. It is more like nested furnaces. Hydrogen surrounds helium. Beneath that, carbon and oxygen. Deeper still, neon, oxygen, silicon, sulfur, and finally, the iron group core. each shell may still be burning, adding new material to the layers below. Silicon burning builds nuclei near iron and nickel. And at the center, the iron group core grows heavier. Iron is the turning point because of nuclear binding energy. Light nuclei can release energy by fusing into heavier nuclei up to the iron group. Very heavy nuclei can release energy by splitting apart. Iron and nickel sit near the peak of stability. They are among the most tightly bound nuclei. A star can gain energy by moving toward them from below, but not by pushing beyond them through ordinary fusion. Once the core is dominated by iron group nuclei, the star has made a center that cannot pay the pressure bill. The iron core is not immediately helpless. It is supported partly by electron degeneracy pressure, a quantum effect that arises because electrons cannot all occupy the same state. When matter is compressed, electrons are forced into higher momentum states, and that produces pressure even without ordinary heat. This same pressure supports white dwarfs. It is one of the great reminders that quantum mechanics is not a delicate laboratory curiosity. It can hold up the corpse of a star. But even quantum pressure has a limit. For a cold white dwarf, that limit is the Chandrasekhar mass, roughly 1.4 times the mass of the Sun, though the exact conditions inside a collapsing stellar core are more complicated than a textbook white dwarf. In a massive star, the iron core grows as shell burning continues. At the same time, the temperature rises so high that photons become destructive. Gamma rays begin to break apart heavy nuclei. This is photodisintegration. It consumes energy instead of releasing it. The star is already short of pressure, and now the remaining energy is being drained. At the same time, electrons are captured by protons. Electron plus proton becomes neutron plus neutrino. The reaction removes electrons, reducing electron degeneracy pressure, and the neutrinos carry energy away. At first, many neutrinos can escape because they interact so weakly. They are almost perfect messengers of the core's catastrophe. The star is losing pressure and losing energy in the same breath. There is no dramatic signal at the surface. No flame breaks through. No outer layer has yet been thrown into space. But the central support has failed. Gravity takes over. The collapse is not like a building slowly sagging. It is closer to a trap door opening beneath the core. The inner region falls inward at a significant fraction of the speed of light. Matter that was already denser than anything familiar is driven toward nuclear density. The radius collapses from thousands of kilometers to tens of kilometers in a fraction of a second. Electrons and protons are squeezed together into neutrons. The distinction between ordinary atoms and the core itself disappears. The material becomes a sea of nuclear matter. For a moment, it seems gravity will crush everything without resistance. But at nuclear density, matter changes its answer. The strong nuclear force and neutron degeneracy pressure resist further compression. The inner core stiffens abruptly. The collapse halts in the center and rebounds. A pressure wave begins moving outward through the still infalling material. This is core bounce. It is one of the most violent reversals in nature. A mass greater than the Sun, falling inward at enormous speed, is stopped and partially thrown back by the stiffness of nuclear matter. The pressure wave steepens into a shock wave. In early explanations, this shock wave was imagined to be the explosion itself, a simple mechanical bounce that would race outward and blow the star apart. But nature is not that simple. The shock immediately runs into disaster. It has to fight material still falling inward. It must halt that material, reverse it, and push it outward. That costs energy. Worse, the shock heats heavy nuclei so violently that photodisintegration happens again. Iron and silicon nuclei are broken into smaller pieces, and every broken nucleus steals energy from the shock. Within milliseconds, the shock weakens. Instead of cutting through the star like a blade, it stalls somewhere above the newborn proto-neutron star. This is one of the central problems in supernova physics. The star has collapsed, the core has bounced, a shock has formed. And yet, in a simple one-dimensional picture, the shock often fails. If nothing revives it, the outer material keeps falling in. The proto-neutron star gains mass. It may collapse into a black hole. The star may fail to explode brightly at all. So the most important question in a core collapse supernova is not whether the core collapses. It does. The question is how the stalled shock is revived. The leading answer involves neutrinos, but not in the simple way one might imagine. The newly formed proto-neutron star is unbelievably hot. It releases most of the gravitational energy of collapse as neutrinos and antineutrinos. The visible explosion, the brilliant light that can outshine a galaxy, is only a tiny fraction of the total energy budget. The bulk of the energy leaves in particles that can pass through whole planets almost as though they were mist. Under ordinary conditions, neutrinos barely interact with matter. But the region behind the stalled shock is not ordinary. The density is high enough that a small fraction of the neutrino flood can be absorbed by the material there. Each absorption deposits energy. One event is tiny, but the star emits roughly 10 to the 58 neutrinos in a few seconds. A small percentage of that flood is enough to matter. The neutrino heating mechanism does not make the explosion effortless. It is not a magic switch. Current theory suggests that neutrino heating, aided by multi-dimensional fluid motion, can revive the shock in many core collapse supernovae. Hot bubbles rise. Cooler material sinks. Convection circulates matter through the heating region. The stalled shock can slosh and deform through instabilities such as the standing accretion shock instability. Turbulence adds pressure and creates asymmetry. Instead of forcing the shock to push outward as a perfect sphere, the star gives it uneven paths, weak points, directions where it can break through. This is why modern simulations are so demanding. A supernova is not a neat spherical explosion. It is a three-dimensional struggle among gravity, nuclear matter, neutrinos, turbulence, rotation, magnetic fields, and the structure of the star before collapse. The broad picture is strong, but details remain active research. Some stars explode readily in models, others are harder. Rotation and magnetic fields may dominate in special cases. The exact boundary between a successful explosion, a weak explosion, fallback, and direct black hole formation is still not fully settled. The caution matters because supernovae are often narrated as if we already know every step with complete certainty. We do not. We understand much of the sequence. We have measured signals that confirm the core collapse picture, but the engine is still a living problem in astrophysics, refined by simulations, neutrino physics, nuclear theory, and observations of real remnants. One observation gave the theory a rare gift. In 1987, a massive star exploded in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. The event is known as SN 1987A. Before the visible light reached its full display, underground detectors on Earth recorded a small burst of neutrinos. Only a few dozen events were seen, but that was enough. Those neutrinos arrived from the collapse itself, not from the later glow. They confirmed that a core collapse supernova releases a vast burst of neutrinos before the shock reaches the surface, and the optical supernova becomes bright. It was like hearing the heartbeat stop before seeing the body fall. When the shock is finally revived, it begins to move outward through the star. It heats each layer as it passes. It drives explosive nuclear burning. Silicon and oxygen layers are transformed in seconds. Radioactive nickel-56 is produced, along with cobalt and iron group elements. The outer envelope is accelerated outward at thousands to tens of thousands of kilometers per second. The star is torn open from within. But even then, what we see as a supernova is not simply the first flash of shock. The light curve, the rise and fall of brightness over weeks and months, is often powered largely by radioactive decay. Nickel-56 decays into cobalt-56. Cobalt-56 decays into iron-56. Gamma rays and energetic particles from those decays heat the expanding debris, keeping it luminous long after the initial shock has passed. The explosion is mechanical, nuclear, and radioactive all at once. From Earth, a supernova may appear as a new star. Historically, observers called them guest stars. A point of light appears where none was visible before. It brightens, sometimes enough to be seen in daylight, then slowly fades. But what the eye sees as a point is actually a vast expanding structure. Stellar layers moving outward, mixing, cooling, glowing, and carrying with them the products of millions of years of fusion. The kind of supernova astronomers observe depends partly on what the star still had wrapped around it when it died. If its spectrum shows strong hydrogen lines, it is a Type II supernova. That usually means the star retained much of its hydrogen envelope. The shock had to travel through that hydrogen, and the expanding debris still carries it. If a massive star lost its hydrogen envelope before collapse, often through intense stellar winds or interaction with a companion star, the explosion may appear as Type 1b. If it lost most of its helium layer as well, exposing deeper carbon and oxygen layers, it may appear as Type 1c. The collapse of the core can be broadly similar, but the outer costume is different. The spectrum tells us not only about the death, but about the life that preceded it. Some Type II supernovae show a plateau in brightness because a large hydrogen envelope recombines and releases energy over an extended period. Others decline more quickly if the hydrogen envelope is thinner. Some show narrow lines when the shock crashes into dense material, the star expelled shortly before death. In those cases, the supernova is not only the explosion of a star, it is also a collision with the star's own recent past. That is one of the reasons supernovae are so valuable. They are not identical fireworks. They are forensic scenes. Their spectra, light curves, neutrinos, remnants, and sometimes gravitational waves or pre-explosion images let astronomers reconstruct the final state of a star that can no longer be seen. But core collapse supernovae are not the only kind. There is another path to stellar destruction, and it begins not with a massive star running out of fuel, but with a small dead star that should have been quiet forever. A white dwarf is the remnant of a star, like the Sun. After such a star sheds its outer layers, its core remains behind, hot, dense, mostly carbon and oxygen, no longer undergoing ordinary fusion. It is roughly Earth-sized, yet it may contain a large fraction of the Sun's mass. It is supported by electron degeneracy pressure. Left alone, it will cool slowly across cosmic time. It will not collapse, it will not reignite, it will simply fade. But many stars are not alone. In a binary system, a white dwarf can orbit another star closely enough to steal material from it. If the companion evolves and expands, gas can flow across the gravitational boundary between them and spiral onto the white dwarf through an accretion disk. Year after year, the white dwarf gains mass. Or, in another scenario, two white dwarfs orbit each other. They emit gravitational waves, lose orbital energy, and slowly spiral inward. After millions or billions of years, they merge. In both families of models, the white dwarf is pushed toward conditions where carbon can ignite under degenerate matter conditions. And this makes all the difference. In a normal star, if fusion heats the core expands and cools, slowing the reaction. In a degenerate white dwarf, pressure does not depend strongly on temperature. The material does not immediately expand to regulate itself. Carbon fusion begins, raises the temperature, accelerates the reaction, and the acceleration feeds on itself. This is runaway thermonuclear burning. In a Type 1a supernova, the white dwarf is not collapsing to a neutron star in the core collapse sense. It is being consumed by nuclear fire. Carbon and oxygen burn explosively into heavier elements, including large amounts of radioactive nickel-56. The energy release unbinds the star completely. Unlike a core collapse supernova, a normal Type 1a leaves no neutron star and no black hole behind. The white dwarf is destroyed. The details are still debated. Some Type 1a events may occur near the Chandrasekhar mass. Others may occur below it, triggered by helium shell detonations that drive a second detonation in the carbon-oxygen core. Some may come from white dwarfs, accreting from normal companions. Others may come from white dwarf mergers. Observations suggest diversity, and the question of progenitor channels remains active. The safe statement is not that every Type 1a supernova follows one neat story. It is that Type 1a supernova are thermonuclear disruptions of white dwarfs or white dwarf systems, and their relative uniformity made them one of the most powerful tools in cosmology. Because Type 1a supernovae often reach similar peak luminosities, and because their light curves can be standardized using the relationship between brightness and decline rate, astronomers can use them as distance indicators. If you know how bright the explosion truly was and measure how bright it appears, you can infer its distance. In the 1990s, two teams used distant Type 1a supernovae to test how the expansion of the universe was changing over time. The expectation was that gravity would slow the expansion. Instead, the supernovae appeared dimmer than expected, meaning they were farther away than a decelerating universe predicted. The conclusion was astonishing. The expansion of the universe is accelerating. That discovery led to the idea of dark energy, a name for whatever is driving cosmic acceleration. But here again, caution is essential. Type 1. A supernovae did not reveal the detailed nature of dark energy. They showed that the universe's expansion history was not what a matter-only decelerating universe predicted. The physical cause remains one of the deepest open problems in cosmology. It could be a cosmological constant. It could involve evolving fields. It could point to something more subtle in gravity or cosmic measurement. Future surveys keep sharpening the test, but the mystery remains. Still, the implication is extraordinary. The destruction of white dwarfs, small dead stars, and distant galaxies became a ladder for measuring the universe. Stellar corpses taught us that cosmic expansion is not merely continuing, it is accelerating. Core collapse supernovae and Type 1a supernovae share the name because both are brilliant stellar explosions, but they are different stories. One is the gravitational collapse of a living massive star whose iron core can no longer support itself. The other is a thermonuclear runaway in a dead compact star. One usually leaves a neutron star or black hole. The other usually leaves no compact remnant at all. One is born from a star's final failure to fuse. The other is born from a white dwarf being pushed into a nuclear runaway after death. Both, however, return matter to the galaxy. After a core collapse supernova, The central remnant tells us how far collapse went. If the remaining core is within the range that neutron degeneracy pressure and nuclear forces can support, it becomes a neutron star. This object is almost impossible to compare with everyday matter. It may contain more mass than the Sun in a sphere only 20 or 30 kilometers wide. Its average density is near nuclear density. A sugar cube volume of neutron star material, if it could exist outside the star, would have a mass comparable to mountains or worse. Such comparisons are crude, but they convey the point. A neutron star is matter pushed to the edge of what nuclei can bear. Newborn neutron stars are hot. They cool by emitting neutrinos. They may rotate rapidly because the collapsing core conserves angular momentum. Just as a skater spins faster when pulling in their arms, a stellar core spins faster as it contracts. Some neutron stars are born as pulsars, rapidly rotating, magnetized objects whose beams sweep across space. When those beams point toward Earth, radio telescopes detect regular pulses. The first pulsar, discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish's group, was so regular that it briefly raised playful speculation about an artificial signal. But more pulsars appeared, and the natural explanation became clear. These were neutron stars, the compact remnants of supernovae, spinning with astonishing stability. Today, pulsars are tools for testing gravity, probing dense matter, and even searching for gravitational waves through precise timing arrays. Some neutron stars have magnetic fields so intense that they form a special class called magnetars. Their fields can be hundreds or thousands of times stronger than ordinary pulsar fields, and perhaps a quadrillion times stronger than Earth's. Magnetars can release giant flares, rearrange their crusts, and radiate enormous amounts of high-energy light. They are not common, but they show that a supernova can produce not just a remnant, but a new engine of cosmic violence. If the remnant is too massive, even neutron degeneracy pressure cannot hold it up. The threshold is often discussed in terms of the Tolman-Oppenheimer-Volkoff limit, but the exact value depends on the equation of state of ultra-dense matter, which is still uncertain. Above that limit, the core collapses into a black hole. Sometimes a neutron star may form first, then collapse later as fallback material adds mass. In other cases, the shock may fail and the star may collapse more quietly into a black hole, producing a faint or failed supernova. Failed supernovae are difficult to confirm because the signature may be a star that simply vanishes. Some candidate events suggest this may happen, but again, caution matters. Not every missing star is a clean detection of direct collapse, and the population of failed explosions is still being studied. What is clear is that the path from massive star to neutron star or black hole is not governed only by birth mass. It depends on the internal structure of the star, its metallicity, mass loss, rotation, magnetic fields, binary companions, and the details of the explosion engine. After the explosion, the debris becomes a supernova remnant. These remnants are among the most revealing objects in the sky because they preserve the shape of the blast and the chemistry of the star. The Crab Nebula, linked to the supernova observed in 1054, is powered by a pulsar at its center. Cassiopeia A, a young remnant in our galaxy, shows knots, jets, and chemical asymmetries that point to a violent, uneven death. SN 1987 A continues to evolve as its expanding debris interacts with rings of gas shed by the star before it exploded. Every remnant is a slow-motion record of a fast event. These structures remind us that supernovae are not finished when the light curve fades. The ejected material travels outward for thousands of years, colliding with interstellar gas, creating shock waves, heating plasma, accelerating cosmic rays, and carving bubbles in the galaxy. A supernova remnant can compress nearby clouds of gas and perhaps help trigger new star formation. It can also stir the interstellar medium, mixing elements across space. The star's death becomes part of galactic weather. The chemical role of supernovae is often summarized in a sentence, "We are made of stardust." The sentence is true, but it can become too easy to say. To feel its weight, we have to ask what the early universe was missing. In the first minutes after the Big Bang, the universe produced mostly hydrogen and helium, with traces of lithium. It did not produce carbon in bulk. It did not produce oxygen, silicon, calcium, iron, copper, iodine, gold, or uranium. The early universe had the ingredients for stars, but not for rocky planets, bones, oceans, or blood. Stars changed that. Through fusion, they built heavier nuclei. Low and intermediate mass stars contributed carbon, nitrogen, and other elements through late-stage winds. Massive stars built oxygen, neon, magnesium, silicon, sulfur, and iron group material through successive burning stages and explosive nucleosynthesis. Type 1a supernovae contributed a major fraction of iron group elements. Neutron star mergers, and perhaps some special kinds of supernovae, contributed to the rapid neutron capture elements such as gold, platinum, and many rare heavy nuclei. The modern picture is more complex than the old claim that supernovae alone made everything heavier than iron. We now know neutron star mergers are powerful sites of arch-process nucleosynthesis, as confirmed by the kilonova associated with the gravitational wave event, GW 170817. Core collapse supernovae may contribute in some environments, especially through neutrino-driven winds or rare magnetorotational explosions, but the dominant sites are still being investigated. The important point is not to simplify the cosmic origin of elements into one event. The periodic table is a record of many astrophysical processes, yet supernovae remain central. They forge, release, and distribute. They are why elements made inside stars escape into the galaxy instead of staying buried forever. A star can manufacture oxygen in its core, but if that oxygen never leaves the star, it cannot become rock, water, air, or flesh. A supernova breaks open the vault. Consider iron. Some iron is made in massive stars, but Type 1a supernovae are major contributors to the cosmic iron inventory. The iron in Earth's core, in human blood, and in old tools likely comes from a long history of such explosions, mixed with material from core collapse supernovae and other stellar sources. Calcium in bones, silicon in rock, oxygen in water, sulfur in proteins, phosphorus in DNA. Each element carries a different stellar genealogy. None has a single simple address. Your body is not made from one dead star. It is made from a chemical inheritance assembled by many stars across billions of years. Some atoms may have formed in the quiet interior of a red giant, some in the shock front of a core collapse supernova, some in the detonation of a white dwarf, some in the collision of neutron stars. Those atoms drifted through interstellar space, mixed into a molecular cloud, became part of the sun's birth environment, joined the disk that formed the planets, entered Earth, cycled through oceans, rocks, air, microbes, plants, and animals, and eventually became you. A supernova is therefore not merely the death of a star. It is one of the universe's methods for preventing matter from remaining trapped in old forms. It is a violent return to circulation. There is a useful discomfort in this. The processes that make complexity possible are not gentle. The oxygen in your lungs did not come from a peaceful universe that carefully prepared it for you. It came through gravity, pressure, fusion, collapse, shock waves, radioactive decay, and the scattering of stellar debris. The universe does not create by avoiding destruction. It creates by transforming destruction into new availability. That is the central paradox of a supernova. The star dies because it cannot sustain itself, but the galaxy lives differently because the star dies. This paradox is visible in the timescales. The core collapse happens in less than a second. The light show lasts weeks or months. The remnant expands for thousands of years. The elements travel for millions or billions of years. A future planet forms long after the original star has vanished. The biological consequences may wait even longer. A single second of collapse can echo across cosmic history. But we should not let the beauty erase the violence. Near the explosion, a supernova is catastrophic. Any planet too close would be sterilized or destroyed. The radiation, shock, and cosmic rays are lethal. A supernova in the wrong place at the wrong distance could threaten atmospheres and biospheres. Some researchers have explored whether nearby supernovae left traces in Earth's geological record, such as isotopes like iron-60 deposited in ocean sediments. These studies are intriguing, but connecting specific biological events to specific supernovae requires care. The influence of supernovae on life is both creative and dangerous, depending on distance, timing, and environment. That duality is important. Supernovae are not benevolent. They are not cosmic gifts aimed at life. They are physical events governed by gravity, nuclear physics, and radiation transport. Life is a later consequence, not the intended purpose. The universe does not need us in order to explode stars. But we need those explosions in order to exist. To see the science clearly, we have to hold both truths at once. A supernova is an astrophysical catastrophe, and it is a cosmic recycling event. It is the failure of a star's internal support, and it is a source of the elements that make future structure possible. It is not a mystery solved by one phrase. It is a chain. Mass sets the evolutionary path. Fusion builds the core. Iron stops profitable fusion. Pressure fails. Collapse begins. Nuclear matter rebounds. The shock stalls. Neutrinos and turbulence may revive it. Radioactive decay lights the debris. Remnants and ejecta reshape the galaxy. Every link has evidence. We see massive stars near the end of life. We observe supernova spectra that reveal hydrogen, helium, silicon, iron, and other elements. We detect remnants with pulsars at their centers. We measure neutrinos from SN 1987A. We model radioactive decay in light curves. We observe type 1a supernovae in old stellar populations where massive young stars are absent. We see nucleosynthetic signatures in meteorites, stars, and galaxies. The picture is not speculation assembled from one clue. It is a web of observation and theory. And still, there are open questions. Which massive stars fail rather than explode? How exactly does turbulence shape the neutrino-driven mechanism? What is the precise equation of state of neutron star matter? What fraction of type 1a supernovae come from accreting white dwarfs versus white dwarf mergers? How do magnetic fields and rotation alter rare explosions? What are the dominant sources of the heaviest R-process elements across cosmic time? These questions do not weaken the story. They make it alive. Science is strongest when it can say both what is known and what remains unsettled. If you could stand outside the galaxy and watch time compressed, you would see supernovae as brief flashes in spiral arms and old stellar populations. In young regions, massive stars would ignite, live short, brilliant lives, and detonate near their birth clouds. In older galaxies, white dwarfs would occasionally cross their own instability thresholds and vanish in thermonuclear fire. Around each event, shock waves would expand, fade, and merge with the surrounding medium. The galaxy would shimmer with death, but over long times the pattern would be constructive. Gas would be enriched. New stars would form from material that was no longer primordial. Planets would become possible. Chemistry would deepen. The Milky Way has likely hosted many supernovae over its history. Most were hidden by dust or occurred before human observers existed. Some were recorded. The supernova of 1054 that gave us the Crab Nebula, the event associated with Tycho's supernova in 1572, Kepler's supernova in 1604. Since then, no naked-eye supernova has been seen in our galaxy, though supernovae have been observed in other galaxies. The next nearby supernova will be a scientific revolution. Neutrino detectors, gravitational wave observatories, X-ray satellites, gamma-ray instruments, optical surveys, and radio telescopes will all turn toward it. For the first time, humanity may watch a core collapse through multiple messengers at once. A nearby supernova would not merely be a spectacle, it would be a laboratory we cannot build. No accelerator on Earth can reproduce a collapsing stellar core. No pressure vessel can hold nuclear density matter. No experiment can release 10 to the 53 ergs in neutrinos. Supernovae give physics conditions beyond human engineering. They let us test matter, radiation, and gravity at extremes. This is one reason they matter beyond the origin of elements. Supernovae are probes of physics itself. Their neutrinos test weak interactions in dense matter. Their remnants trace shock physics and cosmic ray acceleration. Their light curves test radioactive decay, opacity, and radiative transfer. Their compact remnants test gravity and quantum pressure. Their rates and distributions test stellar evolution and galaxy history. Their use as distance indicators tests cosmology. The death of a star becomes a measuring instrument for the universe. And yet, when we return to the simplest image, the whole structure can be held in one thought. A star shines because it is balanced. It dies violently when that balance fails. The failure begins in the core, hidden from sight. The outward brilliance is the delayed consequence of inward collapse. That is why the common phrase, "a star explodes," is both useful and incomplete. It tells you what the eye sees. It does not tell you what the star experiences physically. Before the explosion, there is exhaustion. Before the light, there are neutrinos. Before the debris expands, the core falls inward. Before creation, there is compression. Imagine again the massive star in its final day. Around it, space is ordinary. The light leaving its surface carries the image of stability. Inside, silicon burns at a furious pace. Iron accumulates. The core grows. Electrons crowd into quantum states. Gamma rays break nuclei apart. Electrons merge with protons. Neutrinos begin to flee. The support thins. Then the core passes the threshold. The inward fall begins. For a fraction of a second, the star is two things at once. Its surface is still the star it was, shining with old light. Its center is already something else, collapsing into a proto-neutron star, releasing a neutrino flood that will cross space almost unnoticed. The outer layers do not know their foundation has failed. The universe has a delay between cause and visible consequence, and in that delay, the supernova is already inevitable. The core stiffens. The bounce launches the shock stalls. Neutrinos heat the region behind it. Turbulence grows. The shock finds a way outward. The star that seemed calm becomes unbound. Hours later, days later, the surface erupts into light. To a telescope, a new point appears. To physics, a chain of processes has completed the transfer from hidden collapse to visible explosion. To the galaxy, newly forged and newly released elements begin their long journey outward. To future worlds, the raw inventory changes. This is what happens when a star dies. It does not simply end. It gives up its structure. It releases what its gravity had gathered and what its fusion had made. It may leave a neutron star spinning like a cosmic lighthouse. It may leave a black hole, silent except for what falls into it. It may leave no remnant at all, if the explosion was the thermonuclear destruction of a white dwarf. But in almost every case, the death changes the chemical future of space around it. The tragedy of a supernova is local. The consequence is galactic. We are used to thinking of life as fragile because it depends on calm conditions, stable stars, solid planets, liquid water, gentle chemistry. But those calm conditions are built from violent histories. Earth is possible because earlier stars were not calm forever. Blood is possible because iron was made and released. Bones are possible because calcium was forged and distributed. Breath is possible because oxygen escaped stellar interiors. The quietness of a living world rests on explosions that happened before it existed. There is no need to make this mystical. The physical story is already deep enough. Matter cycles. Gravity gathers. Fusion transforms. Collapse releases. New clouds form. New stars ignite. New planets cool. Chemistry begins. Sometimes on at least one planet, atoms become conscious enough to ask where they came from, and the answer is written in stellar death. Somewhere in the observable universe, a massive star is now approaching its final burning stage. Perhaps its silicon shell is already active. Perhaps its iron core is growing toward instability. Perhaps its outer surface still shines calmly, giving no warning to whatever surrounds it. When the collapse begins, neutrinos will escape first. A shock will struggle outward. If the explosion succeeds, the star will brighten and then fade, leaving debris expanding into space. Long after the light is gone, the atoms it released will continue traveling. Some of those atoms may never join anything complex. They may drift forever in interstellar gas. Some may become part of a cold cloud. Some may fall into a new star. Some may become dust grains. Some may become rock. Some may become ocean. Some may become the chemistry of a living cell. That is the long afterlife of a supernova. Not the brightness, not the brief moment when one star outshines a galaxy. The true afterlife is chemical. It is the slow migration of matter from one generation of stars to the next. It is the fact that an event lasting seconds can become part of planets billions of years later. When we look at a supernova remnant, we are not only looking at debris. We are looking at a transition zone between old stellar identity and future cosmic possibility. The star is no longer a star. The material is not yet a planet, not yet another star, not yet a molecule in a living organism. It is between forms, glowing, expanding, mixing, waiting for gravity to gather it again somewhere else. That is why supernovae occupy such a strange place in our understanding of the universe. They are endings that behave like beginnings. They are catastrophes that make complexity easier. They are proof that destruction and creation are not opposite processes in astrophysics. Often they are the same process viewed at different times. The star does not explode because the universe is dramatic. It explodes because pressure failed, gravity won, and nuclear matter answered. The elements do not spread because the universe is generous. They spread because the blast unbound the star. Life does not emerge because the supernova intended it. Life emerges later because the periodic table became rich enough for chemistry to try. That is a more powerful story than saying the star died so we could live. The star did not know us. It did not choose us. It followed the laws of physics until those laws turned its collapse into a gift no one had asked for. In that sense, a supernova is one of the clearest examples of how indifferent physics can still produce meaning. The event itself is not designed for meaning. It is gravity, pressure, neutrinos, nuclei, and radiation. But the consequences pass through time until matter made in that event becomes part of beings able to understand the event. Meaning appears later, inside the descendants of the debris. When you see an image of a supernova remnant with filaments of oxygen, knots of silicon, arcs of X-ray gas, and perhaps a pulsar shining at the center, you are seeing more than a beautiful astronomical object. You are seeing a record of failure and continuation. The star could not remain itself. But because it could not remain itself, the galaxy did not remain chemically the same. The next time the word supernova appears, do not picture only a star blowing apart. Picture the hidden second before light. Picture an iron core with no fuel left to burn. Picture electrons being forced into protons. Picture neutrinos leaving almost untouched. Picture a shock wave losing its strength, then being revived by a flood of ghost particles and turbulent heat. Picture radioactive nickel keeping the debris bright. Picture a neutron star spinning in the aftermath, or a black hole where the core could not stop falling. Picture a white dwarf in another system, quietly stealing mass until carbon ignites and the entire dead star becomes a thermonuclear flash. And then picture the debris cooling, mixing, and traveling. That is the part most of us forget. The explosion is not the final sentence. It is punctuation in a much longer paragraph. The material goes on. It joins the galaxy again. It becomes available. A supernova is the universe opening a locked room. Inside that room were elements made by pressure and time. Outside, it is the cold space where new clouds wait to be enriched. The door opens violently. It opens once. The star cannot close it again. What it made is no longer private. The elements leave. If we follow them outward, the story becomes less like an explosion and more like a migration. The fastest material races into surrounding gas and dust. It does not move through emptiness in a simple way. Interstellar space is thin, but it is not nothing. It contains gas, magnetic fields, dust grains, cosmic rays, and relic structures left by earlier stars. The supernova debris slams into this medium and forms a shock that can last far longer than the bright supernova itself. In the first stage, the ejecta expand almost freely. The mass thrown out by the star is still greater than the mass swept up from the surroundings. Knots of oxygen, silicon, sulfur, calcium, and iron race outward at different speeds. If the explosion was asymmetric, as many are, the debris is not a perfect sphere. It has plumes, jets, clumps, and fingers where heavy elements from the inner layers have punched outward, while lighter material has mixed inward. The remnant is already telling the truth that the star's death was not smooth. Later, as the expanding shell sweeps up more interstellar gas, the remnant slows. The shock heats the surrounding material to millions of degrees, making it shine in X-rays. Electrons spiral around magnetic field lines and produce radio emission. Dust grains are shattered or heated. Some particles are accelerated to nearly the speed of light. A supernova remnant can become a cosmic particle accelerator, far larger than anything humans can build. This is one likely source of many galactic cosmic rays. The details remain complex, especially at the highest energies, but shocks and supernova remnants are strong candidates for accelerating protons and atomic nuclei through repeated crossings of turbulent magnetic fields. The same event that enriches the galaxy with atoms also energizes some of those atoms into fast-moving particles. Long after the visible supernova has faded, the remnant can still be shaping the radiation environment of the galaxy. Eventually, after tens of thousands or hundreds of thousands of years, the remnant merges into the interstellar medium. Its individual identity fades. The glowing shell dissipates. The chemical signature remains, diluted and mixed. This is how stellar death becomes ordinary gas again. The dramatic object becomes background material, and that background material is what future stars are made of. This matters because galaxies are not static collections of stars. They are ecosystems of matter. Gas cools and collapses. Stars form. Massive stars heat and ionize their surroundings. Stellar winds carve bubbles. Supernovae inject energy, turbulence, and elements. Some feedback suppresses star formation by heating and dispersing gas. Some feedback promotes star formation by compressing dense regions. The result is not a simple machine where every supernova produces new stars immediately. It is a complex self-regulating environment where death, pressure, cooling, gravity, and rotation compete across enormous scales. A galaxy without supernovae would age differently. It would keep more gas cold in some places and less enriched overall. It would lack many of the shocks that stir and structure the interstellar medium. It would have fewer heavy elements available for rocky planets. It would be chemically poorer, dynamically quieter in some ways, and less capable of producing the kinds of complex worlds we know. But supernovae also impose limits. A supernova too close to a planet can be harmful. The danger is not the visible light alone, although a nearby event would be spectacular. High-energy radiation, cosmic rays, and changes to atmospheric chemistry may matter. Researchers have investigated whether supernovae tens or hundreds of light-years from Earth could contribute to ozone depletion or climate effects. Isotopic evidence, especially deposits of iron-60 found in geological records, suggests that supernova material has reached Earth in the past few million years. That does not mean a single nearby supernova caused a specific extinction by itself. The Earth's biosphere is complicated, but it does mean our planet is not sealed off from stellar death. The galaxy touches us. That contact is usually invisible. A dust grain from an old explosion becomes part of a molecular cloud. A cosmic ray from a distant shock passes through your body without you noticing. A supernova remnant expands somewhere behind a curtain of dust. The Milky Way's chemical memory is not written as a clean archive. It is mixed into rocks, oceans, atmospheres, living cells, and the faint composition of stars. Astronomers read that memory by looking at spectra. A spectrum is not just a rainbow. It is a barcode of matter. When light passes through or is emitted by gas, specific wavelengths are absorbed or emitted by specific atoms and ions. Hydrogen leaves one pattern, helium another, calcium another, iron another. During a supernova, the spectrum evolves as the ejecta expand and thin. Early spectra reveal outer layers. Later spectra reveal deeper material. By watching those changes, astronomers reconstruct what elements were present and how fast they were moving. The velocity is read from Doppler shifts. Lines are displaced because the ejecta are rushing toward or away from us. Broad lines mean fast expansion. Narrow lines often point to slower material around the star before it exploded. A single spectrum can tell us that a star had lost its hydrogen envelope, or that its shock is colliding with dense circumstellar gas, or that a thermonuclear explosion produced a large amount of nickel. The dead star speaks through displaced colors. Light curves add another dimension. The rise time, peak brightness, decline rate, and late time fading all carry physical meaning. A plateau in a Type II supernova says something about a hydrogen-rich envelope. A fast decline suggests less envelope mass, or different energy deposition. A Type 1a decline rate helps standardize the explosion for distance measurement. A late flattening or brightening can indicate interaction with surrounding material, dust formation, or energy input from a compact remnant. Then there are neutrinos, which come from the deepest layer. They do not wait for the shock to break out. They escape when the core collapses. In a future nearby supernova, neutrino detectors may receive an early warning before the visible light rises. This would let telescopes turn toward the star before the shock breakout becomes visible. It would also give physicists a direct look at the formation of a proto-neutron star, a process hidden from light by the star's own body. Gravitational waves could add another messenger. A perfectly spherical collapse would produce little gravitational radiation, but real collapses are not perfectly spherical. Rotation, convection, turbulence, and asymmetric mass motions can send ripples through space-time. Detecting gravitational waves from a nearby core collapse supernova would be difficult, but revolutionary. It would let us listen to the motion of matter in the central engine itself. This is the future of supernova science. Not one light curve, but many messengers. Photons from the surface and debris, neutrinos from the core, gravitational waves from asymmetric collapse, radio emission from shocks, X-rays from hot plasma, gamma rays from radioactive decay. Each messenger leaves from a different region at a different time. Together, they can turn a stellar death into a full physical reconstruction. That is why a nearby supernova in our galaxy would be one of the most important scientific events of the century. It would not simply be bright. It would be layered. Neutrino detectors might alert us first. Optical surveys would catch the rising light. Space telescopes would observe ultraviolet and X-ray emission. Radio telescopes would trace the interaction with circumstellar material. Gravitational wave detectors would search for the imprint of the collapsing core. Spectrographs would follow the chemical evolution of the expanding debris for years. Future astronomers would return to the remnant for centuries. In a sense, one star would become a universe of experiments. We should also be careful about the word supernova itself because it covers a family of events, not a single mechanism. There are ordinary core collapse supernova. There are stripped envelope supernovae from stars that lost hydrogen and helium. There are Type 1a thermonuclear explosions. There are electron capture supernovae, likely produced by stars in a narrow mass range with oxygen-neon-magnesium cores, where electron captures trigger collapse before the star builds a normal iron core. There are pair instability supernovae, expected in extremely massive stars, where high-energy photons create electron-positron pairs, reducing pressure and triggering catastrophic contraction and explosive oxygen burning. There are pulsational pair instability events where a star ejects shells of mass and pulses before final collapse. Some rare superluminous supernovae may be powered by interaction with dense circumstellar material, by magnetars, or by other engines. This variety is not a contradiction. It is a warning against one simple story. Stellar death depends on mass, composition, rotation, mass loss, binarity, magnetic fields, and environment. The universe has several ways to destroy a star. Electron capture supernova are especially interesting because they occupy the border between stars that become white dwarfs and stars that undergo iron core collapse. In these stars, the core may be made largely of oxygen, neon, and magnesium. As density rises, electrons can be captured by nuclei, such as neon and magnesium, reducing electron pressure and triggering collapse. The explosion may be weaker than many iron core collapse events. Some historical and observed supernovae have been proposed as candidates, but the category remains under study and not every candidate is settled. Pair instability supernovae belong to a different realm. In very massive stars, the core can become so hot that gamma rays produce pairs of electrons and positrons. Those photons had been contributing pressure. When some of their energy turns into particle mass, pressure drops. The core contracts, heats further, and can ignite oxygen explosively. In a full pair instability supernova, the entire star can be disrupted, leaving no remnant. This may have been more common in the early universe, when very massive, low metallicity stars could form. But confirmed nearby examples are rare or debated. The idea is theoretically robust, yet connecting specific observed transients to it requires evidence. Superluminous supernovae add another layer of uncertainty and fascination. Some are 10 or 100 times brighter than ordinary supernovae. Their power source may not be ordinary nickel decay alone. In some models, a rapidly spinning magnetar deposits energy into the ejecta. In others, the ejecta crash into dense material shed before the explosion, converting kinetic energy into light. Some may involve pair instability. Their diversity reminds us that a bright light curve is not a mechanism. Brightness is an observation. The engine must be inferred carefully. This distinction between observation and mechanism is the backbone of safe science writing. A spectrum is observed. A light curve is observed. A neutrino burst is observed. A progenitor star in archival images may be observed, but the exact interior process is often inferred through models. Strong evidence can make an inference highly credible, but it is still important to keep the latter clear: signal, model, interpretation, limitation. The original shock of a supernova is emotional. The deeper shock is epistemic. We cannot open a star and watch its core collapse directly. We reconstruct the invisible from messengers that survived. That reconstruction is powerful, but it is not omniscience. It is science at its best. Constrained imagination disciplined by data. The same is true for the origin of elements. It is tempting to say simply that supernovae made the atoms in us. That is partly true, but the more accurate story is richer. The hydrogen in your body largely comes from the Big Bang. Much of your carbon may come from helium burning in earlier generations of stars, including lower and intermediate mass stars. Oxygen is strongly associated with massive star nucleosynthesis and core collapse supernova enrichment. Iron has major contributions from type 1a supernovae, as well as core collapse events. Gold and platinum are now strongly linked to neutron star mergers, though the full cosmic inventory may include more than one site. The periodic table is not one explosion. It is a genealogy. That genealogy extends into the earliest stars. The first generation of stars, often called population 3, has not yet been directly observed in a definitive way, but theory suggests they formed from nearly pristine hydrogen and helium. Without heavy elements, gas cools differently. Some of these first stars may have been very massive and short-lived. When they died, they provided the first significant heavy element enrichment of the universe. Their ashes changed the conditions for all later star formation. They made it easier for gas to cool, fragment, and form smaller stars and eventually rocky planets. Our Sun is a later generation star. It contains heavy elements because earlier stars lived and died before it. Earth is not made from first material. It is made from processed material. The solar system is a second-hand object, chemically speaking. Its richness is inherited. Meteorites preserve some of that inheritance in microscopic grains that predate the Sun. These pre-solar grains, formed in the winds and explosions of earlier stars, survived the birth of the solar system and became trapped in primitive meteorites. Some carry isotopic fingerprints of supernova or evolved stars. They are tiny solid witnesses from before our star existed. In a laboratory, a grain smaller than a speck of dust can reveal that the cloud which formed the solar system contained debris from multiple stellar sources. This is one of the most intimate ways astrophysics enters the hand. You do not need a telescope to encounter the ashes of old stars. Some are preserved in meteorites. Some are in the Earth. Some are in you. Still, the human connection should not make us forget the remnant itself. A neutron star is not simply a leftover. It is a new object with its own life. Pulsars slow down over time as they lose rotational energy. Their beams may fade. Magnetars flare and calm. Binary neutron stars continue orbiting, emitting gravitational waves, sometimes merging after millions or billions of years. When they merge, they can produce another kind of transient, a kilonova, rich in neutron capture elements. Thus, the remnant of one supernova can become the seed of another cosmic enrichment event later. The universe reuses its extremes. A black hole remnant also has a future. It may accrete matter from a companion star, producing X-rays. It may merge with another black hole, producing gravitational waves. It may sit in darkness, revealed only by the motion of nearby stars or the radiation of infalling gas. In some massive star deaths, the difference between a visible supernova and a quiet collapse may determine whether elements are returned to space or swallowed behind an event horizon. This is another reason the failed supernova question matters. It is not only about counting explosions. It is about chemical accounting in galaxies. If too many massive stars collapse directly into black holes without ejecting their outer layers, the chemical enrichment history changes. If enough explode successfully, they distribute oxygen and other alpha elements efficiently. Observed abundance patterns in galaxies, ancient stars, and clusters help constrain how often different fates occur. In this way, the chemistry of old stars becomes evidence for the deaths of even older stars. Astronomers sometimes speak of alpha elements: oxygen, neon, magnesium, silicon, sulfur, calcium, titanium. Many are built in massive stars and released by core collapse supernovae. Iron peak elements, especially iron and nickel, receive large contributions from type 1 a supernovae. By measuring the ratio of alpha elements to iron in stars, astronomers can infer the history of star formation in a galaxy. Rapid early star formation produces many massive stars and core collapse supernovae, enriching gas with alpha elements before type 1. A supernovae have time to contribute much iron. Later, type 1a events add iron over longer timescales. The chemical ratios become a clock. Supernovae therefore do not just make elements. They make histories readable. A galaxy's stars carry the record of how quickly it formed, how much gas it kept, how often it exchanged material with its surroundings, and how many generations of stars lived and died. The spectra of old stars are fossils. Their chemistry remembers explosions that no telescope was present to see. This is why supernovae sit at the intersection of many fields. Stellar physics explains how the progenitor evolves. Nuclear physics explains fusion, electron capture, and radioactive decay. Particle physics explains neutrinos. Fluid dynamics explains shocks and turbulence. General relativity matters for compact remnants and gravitational waves. Cosmology uses type 1a explosions to measure expansion. Planetary science depends on the elements they distribute. Biology depends indirectly on the chemistry they make possible. One event touches almost every scale, and yet, the event begins with a simple imbalance: gravity pulling inward, pressure failing to answer. There is a humility in that. Stars seem eternal to human eyes because human lives are short. A blue supergiant may live only a few million years, but that is still far longer than civilization. A red giant may swell and pulse across timescales that dwarf recorded history. Even a supernova remnant can expand for thousands of years, but compared with cosmic time, massive stars are brief. They are brilliant and temporary. They return their matter quickly. The sun is calmer, smaller, and longer-lived. It will not enrich the galaxy with a core collapse supernova. It will end by shedding a planetary nebula and leaving a white dwarf. That white dwarf may cool for longer than the universe has currently existed. The sun's death will be dramatic on human scales, but not supernova-like. This distinction matters because not every star is destined for explosive death. Most stars are not. The galaxy is full of red dwarfs and sun-like stars that will fade or transform quietly. Supernovae come from the exceptional pathways, the massive stars that burn fast, the compact white dwarfs in binary systems, the rare giants that enter pair instability. They are not the standard death of every star. They are the deaths that matter disproportionately because they move so much energy and material so quickly. The universe often works this way. Rare events can shape common conditions. A supernova may be rare in any single galaxy, perhaps only a few per century on average, but across the observable universe, they happen constantly. Their cumulative effect over billions of years is enormous. One explosion is a flash. Many explosions across cosmic time become the chemical evolution of galaxies. So the proper scale of a supernova is not only seconds or light years, it is generations. It is the time between one star's death and another star's birth. It is the chain from primordial gas to enriched clouds to rocky planets to living chemistry. It is the fact that matter remembers energy through its arrangement. There is another way to understand why these explosions matter. They are among the few cosmic events where human history and stellar history can touch directly. Most astronomical processes are too slow to witness. Galaxies rotate over hundreds of millions of years. Stars spend millions or billions of years in stable phases. Planets cool, migrate, and erode across timescales that make civilization look instantaneous. But a supernova can become visible within days. A star that was too faint to notice can suddenly appear to the naked eye. A process prepared across millions of years announces itself within a human lifetime. Ancient observers did not know about iron cores, neutrino heating, white dwarfs, or radioactive nickel. They saw a guest star and recorded its position. Those records still matter. The guest star of 1054 helps connect the Crab Nebula to a historical explosion. Tycho's supernova in 1572 and Kepler's in 1604 helped undermine the old belief that the heavens were unchanging. A sudden new light in the sky was not merely an astronomical curiosity. It was a philosophical wound. The sky, once thought perfect and immutable, had changed. Modern astronomy turned that wound into a method. We no longer simply ask where the new star appeared. We ask how fast it brightened, what elements its spectrum contains, whether it occurred in a young spiral arm or an old elliptical galaxy, whether X-rays reveal a compact remnant, whether radio emission shows interaction with circumstellar gas, whether neutrinos arrived, whether archival images show the progenitor before it died. A supernova is now a time-resolved experiment. The universe performs the experiment. We race to record it before the crucial clues fade. This urgency has changed astronomy. Wide-field surveys repeatedly scan the sky, searching for objects that were not there before. Automated systems compare images, flag transients, and alert telescopes around the world. A supernova caught early can reveal shock breakout, the moment when the explosion's first light escapes the star's surface. That initial flash carries information about the star's radius and envelope. A red supergiant, bloated and enormous, releases the shock differently from a compact stripped star. The first hours may contain clues that will never return. There are also pre-supernova signals that astronomers are beginning to watch more carefully. Some massive stars shed material in the years before they explode. Some show eruptions, enhanced winds, or strange variability. These episodes may be tied to unstable late-burning stages, wave-driven mass loss, binary interaction, or other processes not yet fully understood. The dense material around some supernovae tells us that the star was active shortly before death. It was not always quietly waiting. In some cases, it seems to have been rearranging itself in the final years, as though the interior crisis was already disturbing the surface. But caution is necessary here as well. Not every unstable massive star is about to explode. Betelgeuse, for example, has attracted public attention because it is nearby, bright, variable, and destined to die as a supernova someday in astronomical terms. Its unusual dimming in 2019 and 2020 inspired speculation. Later, evidence supported explanations involving surface cooling and dust, rather than imminent collapse. Betelgeuse will explode eventually, but current science does not say it is about to happen on a human schedule. A star can be dramatic without being in its final hour. That distinction protects the wonder from becoming misinformation. Supernova science is already dramatic. It does not need false countdowns. If a massive star in the Milky Way did explode at a safe distance, the experience would be unforgettable. It might become visible in daylight. At night, it could cast shadows. Detectors would register neutrinos before the optical display peaked. For weeks or months, the new light would dominate the sky. Then it would fade, leaving astronomers to track the remnant for generations. But if the star were too close, the same event could become hazardous. Distance changes, meaning far away. A supernova is a laboratory. Too close, it is an environmental threat. This is one of the reasons supernovae force us to abandon simple emotional categories. They are neither good nor evil, neither gifts nor enemies. They are physical events whose consequences depend on context. A blast that enriches a distant molecular cloud may sterilize a nearby biosphere. The same heavy elements that build future planets are carried by an explosion that can destroy existing atmospheres. Cosmic creation is not gentle enough to be comforting, but it is not cruel enough to be personal. The more precise we become, the stranger the moral language feels. Gravity does not know that it is collapsing a core. Neutrinos do not know that they are helping revive a shock. Nickel decay does not know that it is lighting an expanding shell. Yet after enough time, observers made from the ashes of earlier stars can give names to these processes and trace their consequences. We are late enough in cosmic history to inherit the products of many explosions, and early enough to still see stars making more. This places humanity in a narrow and beautiful window. The universe is old enough for heavy elements, rocky planets, and biology. It is not so old that star formation has ended. We live in an era when the galaxy still makes massive stars and still loses them violently. We can look outward and see the process that made our existence possible still happening. The origin story has not ended. It is ongoing. Somewhere, a molecular cloud is being enriched. Somewhere, a white dwarf is approaching unstable conditions. Somewhere, two neutron stars are spiraling inward because they are losing energy to gravitational waves. Somewhere, a massive star has already built an onion of shells around an iron core. These events are not synchronized for us. Most are too far away to affect us directly. But together, they form the background metabolism of the cosmos. To call a supernova a death is accurate. To call it only a death is too small. It is also a disclosure. It reveals a star's interior by throwing it into space. During life, a star hides its deepest layers. We see the photosphere, not the core. The fusion history is buried. A supernova tears that history open. Oxygen-rich knots, silicon-rich filaments, iron group debris, and radioactive remnants become visible. The star's internal record is scattered across light years. Death makes the interior public. It is a redistribution of energy. The gravitational binding energy of the core becomes neutrinos, heat, motion, and radiation. Most of it escapes invisibly. A small fraction becomes the blast. A smaller fraction becomes visible light. Yet that small fraction is enough to outshine galaxies. This mismatch between total energy and visible energy is one of the most important corrections to intuition. The brightest thing we see is not the main event. The main event is mostly hidden in neutrinos and compact matter. It is a test of matter. At nuclear density, we do not know the equation of state perfectly. How stiff is neutron-rich matter? How does it behave under compression beyond ordinary nuclei? Neutron star masses, radii, cooling, mergers, and supernova dynamics all provide clues. A supernova is connected to this question because the explosion engine depends partly on how the proto-neutron star forms and cools. The boundary between neutron star and black hole is not just an astronomical classification. It is a question about the behavior of matter at densities no laboratory can reach. It is a clock. Type 1, a supernovae track cosmic expansion. The ratios of alpha elements to iron track galaxy formation timescales. Radioactive decays shape light curves. Expanding remnants let astronomers estimate ages and energies. The universe writes time into supernova debris and then invites us to read it. And it is a warning about appearances. A star can seem stable while its core has entered final collapse. A point of light can represent a blast wave larger than a solar system. A beautiful nebula can be the aftermath of violence. A dead white dwarf can become more cosmologically useful than a living star. A tiny neutrino signal can carry more direct information about a stellar core than the visible light that impresses the eye. This is the deeper documentary spine of a supernova. The visible explosion is only the surface of the story. Beneath it is a chain of hidden transformations, and beyond it is a chain of future consequences. That is why the cleanest description is also the hardest to hold emotionally. A supernova begins as a local failure and becomes a cosmic redistribution. The core loses its battle, but the galaxy gains material. The star cannot save itself, yet the matter it releases may help build systems that last far longer than the star did. In the final analysis, the supernova is not a contradiction between destruction and creation. It is the bridge between them. The star cannot keep shining. The core cannot keep resisting. The envelope cannot remain bound. But what leaves the star becomes part of a larger circulation. And from that leaving, everything else becomes more possible.